All right, ladies and gentlemen, let's start our unit on fields today. And we're going to start with our first topic, gravitational fields. So, when we're talking about gravitational fields, we're going to start by talking about universal gravitation. Now, let's talk a little bit about gravity. Okay, so gravity is pretty simple, pretty straightforward. Gravity we always think of as things falling down, but that's not 100% accurate. This all comes down to Sir Isaac Newton. There's a very apocryphal story of Sir Isaac Newton sitting in the apple orchard, the apple falling on his head, and that inspires his theory of gravity. Not quite true. Really, it came down to he was studying the idea of a fellow by the name of Kepler, who was studying the idea of planets rotating around the sun. And from that, he developed the law of universal gravitation that we still use today. So, this is the law of universal gravitation, and it's basically any two objects exert forces on each other so that any two objects actually have an attractive force. So, for example, yourself and the Earth. Now, this amount of force depends on two things. It depends on the distance between the two objects and also the masses of the objects. Now, he also believes that the force acted in a line directly between the center of the objects. For example, gravity doesn't pull down from your head or from your feet, it pulls from your center. We said it's dependent upon the amount of mass. So we put this together into a formula, and with a little bit of extra study, he comes up with this. Now, so it comes down to some sort of gravitational constant times the two masses divided by the square of the distance between the centers of the objects. So let's take a look at this. All right, so we're going to use this formula. And if you remember, I don't think I should put that on there. My apologies. On your worksheet, on your notes sheet, it should say that G is equal to 6.67 times 10 to the negative 11. All right, so I want you to pause, read through the questions, see if you can substitute things into the equation. All right, that's from your notes. Now we have the Earth, which has a mass of 5.98 times 10 to the 24. Masses should stay in kilograms. If they're not, then you need to change them so that they are. Now, to keep things all nice and working well, we're going to make sure any distances are in meters, not kilometers. Now, it says here we're standing at sea level, a distance of this far from the Earth's center. So we're just going to go 6.38 times 10 to the 6 squared. And I'm just going to double check my work. So please pause, multiply that out, and see what you get. Good. So you should get a force of 686 newtons. For reference sake, if you were to take that divided by the 70 kilograms of the one person, you get about 9.8 for his acceleration. So that actually checks out. Okay. Now I want you to try the next example. I want you to pause. Try out that next example using the same equation, almost the same values, except for one slight thing. This distance is slightly different. Okay, so please pause and we will find that force of gravity after the pause. All right, so if you punch everything in, you should get about 684 newtons, which is 2 newtons off from the other one. So the distance does have a bit of an effect. Yes, this means if you're standing on a mountain, you actually have experienced less gravity. So let's take a look at this in a little bit more detail. You guys are going to be doing some interactives. So your first assignment is there's a I should have a handout and I should have a link for the interactives in the folder. And I want you to go through that interactive set with the handout, okay? Awesome. So good luck, and we will see you on the next video.